All right, let's try this one more time. All right. So this is the drone detect project for the UW Engine capstone. My name is David, and I'll be hitting this obstacle.
Thanks, David. I'll talk you guys through a problem statement, which is essentially that drones are becoming more accessible. And so having our own low-cost, portable way to detect these drones is our goal for this project. Additionally, we want to investigate the feasibility of forward scatter radar, which is a less used radar technology, but one that's especially effective for detecting stealth vehicles. And so I'll hand it over to Sean to talk more about the requirements.
Hi, I'm Sean. Talked about the requirements and the objectives. So we wanted to be able to send and receive a sinusoidal signal that complies with the FCC rules and regulations according to our project. We wanted to be able to detect objects that are passing through the baseline that are about 1 foot squared cross-sectional area and approaching the baseline at an angle of 90 degrees. We want to be able to also detect like the velocity and extract other Doppler information and show that in a GUI in real time. I'm going to send it over to Show.
So going forward, we can start talking about our solution concept and design here. So our design here was to use a software-defined radio, or SDRs, with a forward scatter topology. So with this topology here, we have more of a detection fence rather than the traditional omnidirectional radar that you typically think of. Here we have a transmitter and receiver that each have a HackRF, SDR, as well as a laptop connected to them. And from there, any object that passes through that baseline, which is that line right between the transmitter and receiver, you'll be able to detect an object and also extract information such as velocity.
Hi, I'm Joe. Here I'll explain the difference between the forward and the backscatter and why we are choosing to use a forward scatter. Essentially, a backscatter is generally a monostatic radar that is omnidirectional, so it can detect a wide range of area, but it detects the reflection of objects. And like David was mentioning, camouflage objects don't have a reflection. So with a forward scatter system, we're able to detect the shadow of an object, with which any object has, no matter whether it's camouflage or not. So in a forward scatter system, we are able to detect camouflage objects as well. I guess one con to a forward scatter system is that it doesn't have much range, as an object has to pass directly in between the transmitter and receiver setup.
For our SDR, we used the HackRF1, which is an open source hardware project for easily programmable transceivers. Being a transceiver allowed us to transmit and receive using the same 2 pieces of hardware and is easily programmable in GNU Radio, which allows us to control frequency, power, and filters. This made it simple to follow FCC guidelines and restrictions, and the antenna connection made it easy to swap out our antenna whenever we wanted.
Using these HackRFs, there's essentially 2 things that we're mainly trying to extract, which is the power signal and the Doppler signature. The power signal, especially the drop off of it, is going to be how we detect objects. So when we see that power signal fall off a lot, we're going to know that there's an object there. And similarly with the Doppler signature, we're going to be using the frequency analysis of that to detect how quickly that object is moving, and also ideally be able to extract the angle and how far away it is.
For the receive part of our signal processing, we have the HackRFs, which have analog to digital converters connected through USB to our laptops, and that is running GNU Radio, which has software filters like bandpass and low-pass filters and magnitude calculations to extract the power signal. And from that power signal, we have square law detectors and low-pass filters in an envelope detector to get the Doppler signature, which we then use to extract all the velocity information.
So off of that power signal, we can run an object detection algorithm. From here, we use the running average method, in which we have a running average that is used to detect just where our signal noise is without an object passing through. From there, whenever an object passes through, you can see on that bottom graph that the average power starts to dip down. And from there, we can detect that an object has been passing through our system. Once that happens, then we can take a snapshot of that data that passes through, and from there run our velocity estimation algorithm.
I'm shooting for velocity estimation. There are 3 steps. First, we simulate a Doppler signature with different velocity. For the simulated data we got before, generate best fit polynomial function from velocity versus Doppler signature, Doppler spectrogram slope. And for real data, we using the polynomial function we got before, estimates the velocity of it with Doppler signature slope.
So from here, the first step was the simulation of the Doppler signatures. So first, on the left image, you can see a simulated Doppler signature with the cross-section information, which we derived by using some equations from some of the papers that we found. Once we have these different Doppler signatures, we can modify some of the parameters to see simulated Doppler signatures with different velocities. The right two graphs you can see are spectrograms for the Doppler signature at 2 meters per second and at 5 meters per second. And you can notice that the slope of these spectrograms, indicated by that linear green line, is a lot steeper in the 5 meters per second versus 2 meters per second. And analyzing that slope is what gives us kind of the tool to be able to do velocity estimation.
So as mentioned above, as the velocity of the object increases, the slope also increases. And so this graph is the relationship between the velocity and the slope. And you can see that it's a linear fit. So we developed a linear best fit curve that we can use on our real data to estimate the velocity of the objects.
For real data, after doing the signal processing, we got the left graph, and then we calculate the slope of the Doppler spectrogram, the green line. Then we can, using the polynomial function we got before, to estimate the velocity, and then we got 3.6 meter per second.
For our working demo, we set up the HackerOS to set distance apart and ran through it holding a square of aluminum foil. To visualize our data, we developed a GUI that was capable of running through recorded data and pausing when an object was detected using Python.
And so you can see here on this left video is the real data simulations that we did, or not simulations, but the real tests that we performed. And you can see we just had one person running through with a cardboard box with aluminum foil as an object for us to detect. And on the right side is the output GUI data. And you can see here that the average is displayed, and then as the object is detected, the current average dips down. And once it pops back up, we count that as a detection.